Video operating systems. In this lecture, we will be talking about synchronization. We will focus on thread here, and they are sharing the very same address space. Now, imagine that they are accessing to a shared variable, and in this particular case, when they are basically sharing the very same variable, it's okay. Now they are both basically they have like in each of the threads we have basically some part of the code that's basically accessing and changing the contents of here of the shared variable. And here we have another thread, and again this thread has this portion of code which also accesses this shared variable. Now, if you remember, the problem arises regarding this access, and if they are both reading this shared variable, then it's okay. But if they are both writing basically into this, trying to update this shared variables, then we can have some problems. And the source of the reason is that for each of these threads, we have basically we maintain a processor state. What this means is for any shared variable, you basically, in order to update it, you basically copy this into the register, okay, and then you update it here, and then basically you write it back. Now when you do this, it's effectively you are making a copy of this shared variable, updated it, and coming back. Now the second thread, as it's accessing the very same thing, it will also is likely to duplicate it, so it will be again copy this variable from memory into its register. It will update it, and it will try to write it back. Now the problem arises because we can have for this one basically location in memory, I can have two duplicates here, and as a result we can have basically some inconsistencies basically in terms of their values. Now let's basically define things, basically how they work. So we basically talk about this race condition, and what we mean by a race condition is that race condition is something that happens when multiple threads, okay, update a shared variable. If they only read it, then it's no problem, but when they try to update it, then basically it causes a problem. It's because when we are basically updating any shared variable, it requires a minimum of 3 instructions. You basically read the variable into a register, so you copy it into your CPU state, you update the register, and then you move the basically or write back it to the memory. Okay, now the problem arises when we have a context switch between these instructions, and then we can have a race condition. Now as a result of this, remember that when we have multiple threads, the problem is we have this system where we can have the context switch may be happening anytime, so we have no control over that. And as a result of this, when we have a race condition, the concurrent computation may become wrong, because meaning that you may get basically wrong results, and it may be non-deterministic. It means that you will get a different result at each run. And we said it's may because it's not a must, because of the result depends on the timing of the context switch, and this is something that we do not have any control. Now, what we mean, the problem of synchronization is that we want to ensure that the result of this basic computation is deterministic and correct at all times. Now, we had defined basically critical region as the portion of the code that basically updated the shared variable or accesses the shared variable. So if this is our code, and if this is our basically shared variable, then the portion of the code here which basically updates this, that's called the critical region. And if you remember our basically shared apartment example, this shared variable is actually effectively the restroom in the house, and then this part is the restroom routine that we have. Now here's a question that I wanted to think, and which is, in which part of the address space can a shared variable be in? We have the answer to this slide, to this question in the slide, so I wanted to basically think about this. Now the solution that we came up was that if we can ensure that only one thread active in its critical region, then we can solve the synchronization problem. So that was our basic approach to this problem. So we tried using lux to solve this synchronization. And the idea is, if this is my critical region, like here, this is where I update my shared variable, then what I do is I put a lock before entering the critical region, and I put an unlock after exiting it. Now, this is like this basically is very easy to implement, but it looks like it's an easy thing to implement, but we have to realize that this is very difficult. And what we have to do is, how do we implement this lock and unlock? This is not a straightforward problem. So the solution, like one solution that we came up was basically to do spin locking. In spin locking, we basically define a lock variable, okay? And the lock code is basically, it's a while loop, basically checking the value of the lock variable. And if it's 1, then it will loop here in this, this is why we call spin locking, checking the value. And once it returns, then it sets the lock variable to 1 and then enters. And the unlock is very simple, it sets it to 0. Now, this is basically like, this is the idea that, like in this particular case, like in this while loop, is basically you're trying to open the restroom door until you succeed. This is like try, etc. Now, the problem that we had here was that, this lock variable here, that's also a shared variable, and then we will have race conditions. So we are basically back to square one. And if you want to make this work, then we have to make sure that this function should be atomic. What we mean by atomic is that, the code in this basically lock and unlock basically part should not be able to, it should not, well, it cannot be interrupted during execution. This is our basically the main requirement. Now, so the solution is like, how do we implement an atomic lock unlock? Now, there are a couple of basically approaches to this. One is we can have a hardware solution, and the first one is using interrupts. In the interrupts case, like what we can do is lock, we can implement it by disabling interrupts before entering the critical section. And unlock means that enabling the interrupts after exiting that. Now, this is basically, why does it work? It works because we know that preemptive scheduling basically depends on the timer interrupt handler, and which is then used to force a context switch to another thread. Now, we prevent this by basically disabling the interrupts. Now, by looking at how we can implement the atomic lock or unlock, we've found out like there are some hardware solutions like interrupts and atomic instructions, and we also covered basically one software solution, which is Peterson's algorithm. Now, Peterson's algorithm does something that seems impossible, and we have basically covered this in detail. I suggest that you go ahead and look at the slides, and which tell exactly how it works. Basically, in Peterson's algorithm, the race condition happens, but nevertheless, we can ensure that only one thread gets into the critical section. This is very important, okay? And that means that we can have mutual exclusion in the execution of critical section. And we have also seen that like this algorithm can be extended to n threads, and as long as we know what n is, that is the number of threads are known beforehand or a priori. Now, we have seen that spin locking provides a solution to the synchronization problem, but it is not very efficient. And so what we will do is, now we will look at more powerful mechanisms that are basically more efficient, like mutex and semaphores. Stands for mutual exclusion. Now, it's a synchronization primitive that again provides basically lock and unlock mechanism, okay? And what a lock does is, if a thread fails to get the lock, it should sleep. Now, sleeping means that it is removed from the ready queue so that it doesn't consume the CPU by spin locking. So this is a major improvement over our spin locking solution. And in the case of unlocking, when a thread unlocks, it basically wakes up a sleeping thread if there exists one. That is, it inserts the sleeping thread, back into the ready queue so that it can then have access to the CPU as a resource. Now, as we will learn to, as we've already learned, mutex is equivalent to what we call a binary semaphore, which is a more powerful form of this idea. Now, semaphores, this is a horrible looking basically term, but this is a very higher level synchronization construct that was proposed by Dijkstra. It is a shared counter, and it is initialized after we declare it. And we have two operations on the semaphore, and these operations have different names, but we will be using with wait or signal. But wait also means down, or P from Dutch as proposed by Dijkstra. And what wait or down means that it's an atomic action, and it waits for a semaphore value to become 0 and then decrement it. And then signal means or post or up or V. It basically increments the semaphore value by 1. Now let's remember what we have basically done by this. So this is a case like a semaphore is essentially, you can envision it as a table, okay, with a number of tokens on it. So when we initialize a semaphore with 1, it means that initially we are putting 1 token on the table. Now when a first thread comes, and when we say like there is 1, we say that the semaphore value before is 1, and a thread basically calls wait on it. When a thread calls wait, it takes the token if there exists one, and it proceeds. After that, the semaphore value becomes 0. Now, if we have another thread that now calls wait, it comes, and there are no tokens here, so it basically sleeps here. Now, in this case, we say that the semaphore value dropped from 0 to -1 to indicate that there is one thread that's sleeping on the semaphore. Now here we have a third thread comes with a signal. So it comes and then it drops a token, it moves ahead, and then that drop token here, it basically woke up the thread so that it can then move on. Now we can see that in this case the semaphore value basically is changed from -1 to 0, meaning that there are no tokens, but there are also no sleeping threads on it. And if we have thread 4 which comes, then it comes here and then it drops the token and it moves away. Now in this case we are back to our value of -1. So this is the once we understand basically this metaphor, it's very easy to understand basically why it's called up or down or signal and wait. And you can realize that when we have a signal basically always proceeds. So we can write it here. Now a signal, let's see this, here we have signal, okay, it always proceeds, okay. A wait, it depends on what we have on the, like what the initial value of the semaphore is, okay, whether we have tokens here or not. So it may or may not block, okay. That's the main idea. Now let's move on. As we have discussed, we have solved a number of problems in our webinar last time, and you may have realized that like the semaphores, it's a very powerful basically synchronization concept. And the main basically power of that is that, you know, when we have this wait and signal basically calls, that these are unmatched. For example, consider for example the barrier example where we have the wait and signal are very different. Now this is different from like, you know, other locks that we have seen, where we have lock or acquire or release, where these guys are always paired but their power was limited. So this means that, you know, semaphores, it's more powerful, but also it's a lot easier to get into trouble, that we may end up in basically like, you know, writing code that is basically leads up to deadlocks, as we will learn later. And it would be nice, given that this synchronization problem is so common, that if you had some clean and well-defined language support for synchronization. And this is something that some modern operating systems provide support, like Java. And we will see basically. That brings us to the main topic of our lecture. So we will be talking about monitors, okay? And what we mean by a monitor is it's basically extends the semaphore idea into a class. And a monitor is essentially an object, or you can see it as a class with some data and methods encapsulated into one. So this is our monitor, okay, and we have some shared data we want to control access to, and we have some methods you can see here, okay, that basically access this shared data, okay. And a monitor ensures that the methods are executed with mutual exclusion. This means that only one thread can be executing any of the methods at any time, so we can only have one thread here. What if we have another thread comes here? It will be blocked. So this is identical to what we call social distancing nowadays, okay. So if one thread is in the monitor, and all the other threads should wait outside. Now, as such, you can imagine that like in the monitor case, this is basically like when a programming language provides supports for this, it sees how this can be implemented. You can imagine that like once you declare something a class as a monitor, then you basically the programming language can insert locks and unlocks at the beginning and at the end, because these are the critical sections, and that would basically make things easier for us. But we also have, like, along with the monitor, we have another concept that we need to understand. That's called a condition variable. Now, conceptually, a condition variable is equivalent to the thread waiting list of a semaphore. And in the case of a semaphore, if you remember that, like when we have a thread that comes to a semaphore with no tokens or with zero value, then it will, or like a negative value, it will block itself, and then it will wait until another thread comes. So this is essentially the same idea, that when we have like a thread that comes in, okay, and it does some stuff, and then it cannot complete, then it can basically wait and sleep on some queue. This is associated with this monitor, and we will see basically how it works in an example. So this is the case where we have that, like we have this shared data, we have the methods here that access them, we ensure that only one thread is active, and all the other threads which wants to basically execute any of these uh, methods should wait here. Now, so there's at most one thread should be active. Now we can imagine that this is basically similar to a lock, but it actually has more than this. Now let's consider basically a bank, okay? So this is an example that this is our monitor here, the whole building, and we have some shared data. In this case, we have this Turkish lira that's deposited in the in the bank. Now, along with this, we also have basically two methods, deposit and withdraw, okay? And these are methods that access this shared data. And then we have basically a conditional variable. Now let's see how it works. I will draw the thread like as somebody's head, okay? Imagine this is a kind of a bank. This guy comes in and there's no one else, and so he gets in here, okay? And when he gets in, then he can basically he gets in because he wants to use one of the methods. So he says, let's deposit some money, okay? And he deposits some money, and let's say that initially it was 0, so we put basically 100 lira, okay? And when he's in here, by the way, then before getting up, then at this time, imagine that a second thread, let's call them 2, so let's call this guy is 1, okay? This thread comes and he will be blocked, okay? He will be blocked here. And when this guy is done with his job here, then he basically moves out, okay? Now 1 is here, let's remove its okay, good. Now when he moves away, then this guy wakes up, okay? He gets in, okay? He is in here. Now he can now do like execute one of the methods. And let's say that he wants to withdraw money, okay? And this guy wants to withdraw how much? Let's say that he wants to withdraw 200 liras. Now we have only 100 liras, so that means that he has the lock. Now he is active in here. He has the lock, okay? But he cannot complete his task here because there's only 100 lira. What do we do? Now we can imagine that there may be one more guy here, let's call him number 3, who is waiting at the entrance. He may be depositing money so that he could complete him. But since this guy is in here, and since this is a monitor, the third guy cannot actually enter. So what we will do is like a 2, it cannot complete its job. Okay, so it will then basically move into this waiting room, which we call conditional variable. So we can say that this is the waiting room. Okay, so number 2, okay, moves in here and then starts sleeping. Okay, so let's remove his traces here. So he wants to get 200 liras, and once he moves into the waiting room, then this third thread can come in. He would come in here and he would say that, let's say that he wants to deposit money, and he deposits, say, 200 lira. Okay, and as a result, now we have in here, now we will have 300 liras. You can see that. And then once he is done, he should get out. Okay, but on his way out, he should actually notify these guys who are sleeping on this half Turkish lira conditional variable, and then he should wake them up, and then so that they can go ahead and check whether they have enough money or not. So when number 3, okay, in this case, when number 3 gets out, okay, here, so number 3 goes here and he gets up, then basically 2 wakes up, okay, and 2 then moves in here. Okay, now 2 was trying to withdraw 200 liras, right? So he was executing withdrawal, and after that, now he would find 300 liras. He would then complete his job. Now that means that I have only 100 lira left, and then he would then go ahead and then he would then be done. Okay, so this is the idea of a conditional variable. A conditional variable is basically a waiting room, okay, in which threads that cannot complete their job would wait on a condition. Okay, in this case, our condition was have sufficient Turkish lira. Okay, that's the idea. Now let's, and here we have our shared variable. This is the deposit that we have in the bank. Here we have our condition variable, and then we have these 2 methods. One is withdraw. Okay, oops, let's go back. One is withdraw, okay, a certain amount, and the other one is deposit. Now when we want to withdraw a certain amount, then we check whether this amount is larger than the current deposit. If that is the case, it means that the bank does not have sufficient money. As a result, we have to wait on this half Turkish lira condition. Okay, this is where basically the thread would basically moves into the half TL waiting room. Okay, or we can also say that basically the thread basically sleeps on the condition have TL. Okay, so it will block here, and when it wakes up, then okay, then it can, if this is not the case, if the amount was like that, then it will be then deducted from this and it will exit. What about the deposit? In the case of deposit, you're depositing some money, you add it to the current account, and then you do a notify. You can realize that this notify here is effectively a signal, basically, that is associated with this wait signal. Okay, so if a thread is sleeping on here, this notify means that thread wakes up other threads that may be sleeping on this condition. Okay, so this is the idea, that we have this notify and we have the wait thing. And it's nice, you can see that when writing code in the monitor is actually easy, because we are by default we are ensured that only one thread can be active within the monitor. Okay, so we don't have to worry about any kind of synchronization issues, and all we have to do is this wait and notify signals. Now we have to be a little bit careful. In this case, we said that it's if here, okay. Now, and but you can imagine that this is not sufficient. Now consider a case in here, like we may wish to check, replace this if with a while. Why? Because imagine that initially in our bank, say that I want to, for example, we have this. Let me draw this. Okay, so we have this half TL, and our guy, this number one, he wants to withdraw how much? He wanted to withdraw 100 liras, right? Okay, and we didn't have any money here. So what if a guy like this third number three comes here and he deposits 10 lira? Okay, let's just say he deposits 10 lira. Okay, now and then he wakes him up. Okay, when he wakes him up, can he go ahead and finish his task? No. So what it means is when he wakes up and this guy wakes up, okay, when number one wakes up, he has to check whether the money is sufficient here. Okay, and this basically this while ensures this. It waits in here. When it wakes up, it checks that the amount is basically whether the amount is less than the what's deposited here. If that's the case, if there is still not sufficient money, then it will go back and into the waiting room. So this wait basically ensures that when one comes here, like three deposited there, so three basically is done here, and then one comes back to here and he checks, well, it's still not sufficient money, so he goes back to sleep. Okay, so this while ensures that it doesn't basically you don't you check your conditions again. This is the first thing. And the second thing that we have to do is that we have to change that we want to not only notify one, but we want to notify all the threads that are waiting for that. Now, why is that the reason? Now, let me again go with this similar example. Okay, so here we have that. Let's okay. Here is our case, and in this case, imagine that we had just 0 lira. Okay, in here, so we have just 0 lira, and the first guy comes. He wants to withdraw some money. There's none, so he sleeps on here. So number one, and he's sleeping. He needs 100 lira. Okay. Number two comes. He wants to withdraw more money, and then now, let's say he wants to withdraw 200 lira. So again, he also sleeps in here. And then a third guy comes. This guy is rich. Okay. So the third guy comes and he basically withdraws. Well, he deposits, say 1,000 liras. Okay. Okay. 1,000. Oops. Okay. Now, in the previous case, if he had notified only one of them, then this guy would still sleep here, okay? Although there's sufficient money. So in this case, when he deposits money, he has to make sure that he wakes up everybody in the waiting room so that maybe they will all be able to complete their tasks. So that's why we need to have this notify all here. Otherwise, we may have basically threads that will continue to sleep here, although there's money in here. Okay, so now we can work on the same idea, but we can have Turkish lira and US dollar. Okay, we can again run deposit and withdraw, and in this case, depending on your task, okay, if you want, for example, say that we have 0 lira and we have 0 US dollar, okay, and if this guy wants to say deposit money, he would maybe deposit 10 lira and then he gets out, okay, and then the second guy comes, okay, number two, he wants to withdraw say some US dollar, we don't have any, so he will be blocked and he will be then sleeping on a different condition, so we want to put him here into number two, okay, so he will sleep in here, and so let's go ahead. When he's done, and let's say that the third guy comes, okay, now he may be depositing money in here, and in this case he will be, when he deposits money, if there's anyone here, then he will wake them up. If there's no one in there, then this notify signal will be lost and he will be exiting, and this guy will still continue to hear. So you can see that with this, it's very easy to basically talk about how we can control access to these shared variables in a very controlled manner. Now, there's this issue that when we have, like, you may have realized this, but when we have this case that we had the money here, let's say that this is Turkish lira, okay, and say we have 100 lira, and here we have our deposit and withdraw functions, and here's the our FTL, and this guy is, say that number one is sleeping here, okay, and then here we have, now when he's sleeping here, let us, oh sorry, let me just delete this, and let's say that I had just 0 there, okay. So number two comes here, and number two then deposits money, okay, and let's say that he deposits some, like, 100 lira, and then he wakes this guy up, okay. Now when he wakes this guy up, now there's a dilemma. Who will continue execution? So this number two is active, he's still not done yet, okay. So if the number one, if he gets in here, then we'll have a problem, because now in that case, if one comes here, then if one moves here, then I will have one and two at the same place, okay, and this is against the idea of a monitor, okay. So this is a problem that we have here. So there are two possibilities in the and these two possibilities are basically are implemented in different monitor types. So the first one is basically to notify, basically we have this OR monitors that was first proposed. When we say notify a condition variable, it means that the we would run the waiting thread immediately, okay. So in this case, if number two does a notify, then he would wake him this guy up, okay. So one comes in here, okay, and when he is active there, now in the meantime we put number two here, okay. So then one comes here and then completes his job and leaves, and then this guy will come, okay. This is the OR monitors. And then there's the second type, which is the MESA monitors. So this is, in this case, when we do a notify, the waiting thread is then put back into the ready queue for the monitor, but the notifying thread keeps running. Now let me just show them in a better example, okay. So in OR monitor semantics, when we do a notify, and by the way, what I mean by notify is like appears as signal here, it's the same thing. So we have this, basically let's call this number one, okay. When it does a signal, and let's say that it's, and in this particular case, this region here, this region here, this region is the main region that we do work, okay. And we have then two conditional variables, like one on A, so this is the waiting room, this is the conditional variable for A, okay, and this is the conditional variable for B, okay, and this is the main address, okay. You can see that, like, I have, like, threads waiting here because this number one is active here, and these are the threads. Let's say this is number two, okay, and number two and three, they got in and they were not able to complete their task, so as a result they called a wait on A, and they moved in here and they are now sleeping here, okay. Now let's say that the number one does a notify A, okay. When it does our signal, this is the same thing here, when it does a notification, in the OR case, it immediately moves out into here. So now basically one gets here, okay. And once it signals, then numbers, like in this case, one of them is picked up, and like number two, it doesn't matter, and then one of them will be allowed into this basic main room. Now we can have, for example, 3 in here. Now 3, as a result of this, then he will try to complete its job. If it completes its job, then it would leave here, okay. And when it leaves here, when it leaves there, then as a result, after this, like, this number 3 is gone, okay, this guy is gone, okay. And now after that, like, here the number one can come in and he can then complete his job, okay. So number one comes here, he will complete his job, and then he would leave, okay. This is the main idea. So the main reason basically is that, in the OR case, when we do a notify, it causes the notifying thread to block, okay, and it basically waits outside, and then the guy who wakes him up like that this number's 3, then he would then do his job immediately. Now what about the case in the Mesa case? Now this is the other version. In the Mesa case, it's actually it's interesting. In this particular case, like here we have again, like here we have this main entrance. This is where we have maybe where we do our job, okay. And here's our number 1 here, okay. And we have 2 waiting rooms, okay. They are drawn separately, but it's the same thing. And let's say that we have number 2 is here, number 3 is here, and maybe number 4 is here, okay. They are like 2 and 3 are waiting on A, and 4 is waiting for B, okay. Now when number 1 basically notifies, for example, when it says notify, for example, A, okay, and what it means is, as a result of this notification, one of them, and it may be the case in this case, like this 2 would be moved into here, okay. So this guy will be gone, okay. Now 2 is in here, and in this main entrance, it is still not in. After the notification, then 1 continues his job. After it completes, and he would leave here, okay. When he leaves this, okay, then one of them, maybe this number 2, or maybe this new one or a new one, then one of them will get in, and then basically tries to complete this job. And if it cannot complete, then it will again do a wait. Oh, wait, there's a, okay, this should wait A and this should wait B, okay. So we then go in here, okay. So you get the idea. In the Mesa case, the waiting thread basically it puts the waiting thread back into the ready queue, which is like this. In this case, the ready queue is the entrance of this monitor, but the notifying thread keeps running, okay. And this is basically very important. Now why is this important? It's because when you're writing the code, you have to make sure in here. So let me just go back to here. Yes, okay. So in the OR style semantics, okay, the condition that triggered the notify will always be true when the awoken thread runs, okay. For example, if you wake the thread because we had put in something into the buffer, it's for sure that the buffer is no longer empty. In the Mesa case, however, the thread that just woke up has to recheck the condition, okay, because another thread may have gotten and basically then to change this situation, okay. This is the main problem, the difference between them, okay. So when we do here, like we have to be very careful about things. For example, in here, when we do a wait in here, okay, and we need to do this with a while, it's because like if there is like if it's when we wake up from here, we may want to change this condition again, okay, and then before we move on. If we had done this, then maybe some other thread may have removed the item from the array before us. So this is basically a problematic case, okay. So basically, in most textbooks we have OR style, and basically it's basically this idea. And in Mesa style, it's basically in reality in Java and most real operating systems, this is basically what happens. The signaler, the thread that does this notification or signaling, keeps the lock and the processor. The waiter is placed on the ready queue and with no special priority. So basically, you need to check the condition after each wait. This is the very important thing. Now let's see how we can solve our problem. Remember that we had discussed our readers and writers problem, okay? And in that case, you can remember that if we had a database here, and in this database we can have at most one writer at a time, or we can have basically multiple readers, R1, R2, R3. So these are all allowed, okay? Whereas we should not allow 2 writers, like this case, or we should not allow a writer and a reader simultaneously accessing. So this is not allowed, okay. So these are the correctness constraint, and we have solved this with semaphores. Now let's see how easy the things become with to solve this with the monitors and condition variables. of variables. Okay, so the n readers, it's the number of active readers in the database, and writers, like they are both initialized to 0. That's the number of active writers. Then we have these waiting readers and waiting writers. These are the number of waiting writers and readers. And we have two condition variables, can read and can write. Okay, now let's see how it works. So this is the template that we have here. So here we have this, we define this readers writers as a monitor. Okay, and with this monitor, then we define four methods: begin write, end write, begin read, and end read. Okay, so what the thread has to do is, like, it calls begin write, and after begin write, then it writes, and then when it's done, it does an end write. And the same thing with the readers, it calls begin read, after it returns from that, then it can read, and then it does an end read. And here we have our basically the variables can read and can write. Now let's see how we can solve this. Okay, so the first thing that we have to do is, like when we do a begin write, we set, like at the end of begin write, we set end writers to 1. Now we can also, instead of this, you can say end writers plus plus, but we know that the number of writers will be at most 1, so that's why we have set it to 1. Okay, and when we have the end write, then we set end writers to 0. Okay, that's really at the beginning of this. And with the begin read is we increment the number of readers here, and you can remember that we can have multiple readers, so this will go positive, and at the end read we do a decrement. That's pretty straightforward. Okay, now in the end case, let's look at what the writer does. So when we are ending and when a writer exits, now it can check, like, now what it has to do is, when it's exiting, then it has to notify other threads who may be waiting for the database. So we can do, now in this case we said if waiting readers, if there are any waiting readers in this, then we can say notify can read. So it will wake basically a reader, and then so that it can then continue its execution. Else we have notify can write. You can imagine, now you can ask the question, why is this the order, like, why, and you can, and this is a matter of policy, you can change the order, but in this particular case we are basically, the writer is giving priority to the readers than to the writer. So this is a matter of policy, there is no right or wrong. Okay, now in the case of end read, and in this case we check the number of end readers. Then if the number of end readers becomes 0, then we do a notify can write. Okay, now you can remember that if you have, like, like it's like the auditorium example that we had seen in the class, that it's when if you're the last reader, then you can then notify the writer so that he can wake up and continue his job. Okay, that's the idea. Now let's look at the begin write and begin read case. In the begin write case, what we do is that we check whether the end writers is 1 or whether the end readers is 0. Now if this is true, it means that the database is busy and we should wait. Okay, so we add ourselves into the waiting writers, we increment it by 1, and then we do a wait can write. Okay, this is effectively meaning that, well, I cannot complete my method, I cannot complete my task, so I will wait on this can write condition variable. Okay, and when it wakes up, then it will decrement it, and it will get in, and it will go ahead. Okay, what about the readers? In the case of readers, you again check whether the number of writers is 1 or the waiting writers is greater than 0. And in this case, then it would increment the waiting readers, and it would then do a can read wait on, and then if it wakes up, it would decrement it by 1, and then do that, and then finally it would then notify can read. Okay, why does it do this? It means that once it enters here, it should notify other readers such that they can also wake up and get into and do their reading. Now, in order to understand this, like, we can look piece by piece. So, like, the first thing is that we have to ensure that the writer can enter if there are no active writers and no readers are waiting. Okay, so we can look at here. So this is the case that if the writer here, it can begins write if there are no writers and no readers. Okay, in that case, like if that's the case, and it will jump here, and otherwise it will be reading here. Okay, and we also said that a reader can enter if there are no writers active or waiting, and this is again a matter of basically policy. This is what we define. So we can have many readers active at once. Otherwise, the reader waits, and maybe many waits in here. So this is the case where we have that, if the writers is one, and if the waiting or the waiting writers are basically greater than zero, this is basically giving priority. The readers are giving priority to the writers if they and then that's basically, then we execute this. Okay, and we can do a waiting reader. Okay, and when the writer finish, it checks to see if any readers are waiting. If so, it lets one of them to enter, and that one will let the next one enter, and so on. So this is the case where we have seen in here that within the readers, like you basically increment and you notify the next reader. Okay, and so when the writer came, so when we do this and write, so the writer exits, it sets it to 0. If there are waiting readers, it would notify one reader. Okay, what if there are two readers? Well, this reader, once it wakes up, it was waiting in here, so it would come here, and then it would issue another can read. Okay, and it would wake the second one, and the guy that wakes up, then he will come here and he will do another notification. So this is essentially basically starts a chain reaction that all the waiting readers will wake up and basically get into their reading. Okay, so basically as a whole, if a writer is waiting, then the readers queue up, and if a reader or another writer is active, then the writers queue up, and this is mostly fair. And but you can, although once it lets a reader in, then it lets in all the waiting readers at once, and even if some of them showed after basically other waiting writers. So this is the basically thing that we have. Now let's look at monitors, condition variables versus semaphores. Now condition variables are not exactly semaphores. You have to be very careful, but you can note that we can use condition variables and monitors to implement semaphores, or we can use semaphores to implement monitors and condition variables. So we can use them to implement each other. Now you can note that the access to the monitor is controlled by a lock. Okay, and when we have in this, like in the case of a wait, okay, like the semaphore, like it blocks the calling thread and gives up the lock. In the monitor, to call a wait, okay, the reader has to be in the monitor and has the lock. In the semaphore, the wait just blocks the thread on the queue. Now, in the signal case, we know that in the signal case, it causes a waiting thread to wake up. Now, here is the main difference. This is very, very important. Okay, let me just talk here. Okay. In the monitor case, if there is no waiting thread, the signal is lost. Okay, meaning that if there is no one waiting on that particular condition variable, and if you see the send a signal or notify, in this case, this is equivalent to notify. Okay, notify. Okay, so in the case of a monitor, if there is no waiting thread, the signal is lost. In the semaphore case, the signal increases the semaphore count. It's basically putting another token on the table, and so even if there is no thread is waiting, then it will basically it can be used by another thread, which can come later. Okay, so the condition variables have no history, and whereas in the case of a semaphore, nothing is lost. Okay, and actually this is the due to this reason that sometimes semaphores is still it's more tight, and it's actually you have to be more careful into sending in notifications or signals with the monitors are being used in Java. In Java, every object is essentially a monitor. Okay, and what we do is for each object, we define certain methods as synchronized. Okay, and this is the keyword, and it by itself, when you do this, so only one thread can be executing a synchronized method at any time. And the nice thing is, once you can mix synchronized and unsynchronized methods in the same class, and this only applies during the execution of the synchronized statement. and every object can be treated as a condition variable. When we call for a wait, the current thread is suspended, and when we call notify, essentially what we do is the Mesa implementation. You remember the Mesa implementation is used. What it means is when a thread calls notify, okay, it notifies an arbitrary thread from the waiting list, okay, and puts them into the entrance, and then it will continue to work as if nothing has happened, okay, and the notified uh, thread would try to get in and complete its job. And of course, notify all would basically notify all the suspended threads waiting on that particular case. Now, here's a simple example of code. Here we have this counter code, and here's the count, which is the variable that we are interested in. Now we have this increment function method, which is declared as synchronized, which increments the count by +1, and we declare basically C and D, two shared objects. Now if you are interested only in C, then in thread A we just call C increment, and here in B we call C increment. Now despite the fact that we are running both of them at the same threads, since we have declared this as a synchronize, this whole thing acts as a monitor, and only one of the threads can be executed in this particular code, this particular method. Okay. Now, as it is, you may jump to the conclusion that a synchronized method is equivalent to critical section. It is not. Okay. Now, in synchronization, like in this particular case, when we call synchronized, it is associated with the object instances, not the code. This is very important. So when we had declared C and D as two shared objects, the C increment can actually be executed simultaneously with D increment, because they are different instances of the very same object. If it was a critical section, then this would not have been possible. Now let's look at the producer consumer example implemented in Java. In this case, we have this buffer, this class declared as like this is a class, it's buffer, and here's where the data is located. Here we have a count which keeps track of the number of items in the buffer. Okay. Now we declared two methods. Okay. One of them is insert, declared as synchronized here, and so this is R. And the other one is remove, and declared again as synchronized. And in here we have in this while loop, if the count, meaning that the number of items in the buffer equals to the buffer length, it means it's full, then we do a wait, we do a try wait, and as a result of this, it will sleep. It will sleep until it catches an interrupt exception, okay, and when it gets that, then it will get out, and then it will come back and it will check whether the buffer is still full or not. If it's full, then it will wait again, okay, and if it's not full, then it will go ahead and it will produce one basically character, put it into the buffer, increment it, and then we'll do a notify. Okay, and in this case, when you do a notify, it will basically notify any other thread that is waiting in this basically class for this particular case. And here we have the remove part. Again, in this case, when the count is 0, it means that there are no items in the buffer. It will do try await, and until it gets an exception, and this exception is likely to be obtained from the notify. So this notify, and let me just try to do this here. So this notify will actually basically cause this exception. Okay, and when it happens, then it will execute this, and it will basically then remove one character and then print this out, and then it will do a notify, and in this case this notification will again now basically create this interrupt, okay, which will wake the other guy up. So in C, monitors are not provided, but it is very easy to implement, and as a matter of fact, some condition variables are provided as part of this thread library. So here's how we can define a condition variable, okay? And there's an initialization routine. Now here's the part where you generate a signal. This is equivalent to the notify in Java, okay? And you also have the possibility of broadcast, which is equivalent to notify all in Java. And then we have basically this wait, which is exactly what we do, and then wait on a condition. And then there's also the timed wait, which is basically it will wait for an absolute time that is specified in here, okay? And after that it will return an error, okay? And this is how we can generate the destroy a condition. So the point is, synchronization is a very difficult thing, and basically getting it right is pretty hard. Okay, and how do you pick between logs, semaphores, CVS monitors? Where logs are very simple for many cases, but may not be the most efficient solution. And we know that they have limited, for example, in the readers writers case, then we will have a problem. And condition variables, basically they allow threads to sleep while holding a lock. In this case, it's a lock for the monitor. Okay, but so this gives a lot of flexibility, but you have to make sure that whether this condition variables basically they use MESA or OR semantics. And semaphores they provide pretty general functionality, but it's very easy to screw things up. Now, here is one problem that I would like to work at home. It's called the Barbershop. This is actually an exam question from a previous like final or second mid or first midterm. So in this case, we have a barbershop, and this is kind of like how it looks. We have a barber, okay, and we have a set of chairs, and we can have like we have n chairs, and we have one basically barber chair. If there are no customers to be served, the barber goes to sleep. If a customer enters the barber shop and all chairs are occupied, meaning that it's full, then the customer leaves the shop without getting a haircut. If the barber is busy, meaning that it's giving a haircut also to someone, but chairs are available, then the customer would sit in one of the free chairs. And if the barber is asleep because there were no customers, then the first customer would wake up the barber. So here is a basically simple template for this barbershop problem. We have two conditions, waiting for customers and waiting for barbers. Okay, and waiting basically keeps track of the number of waiting customers in the chairs. And this one is like, let's just do this here. So here we have this basically barber thread, okay, which will do some synchronization, and eventually you want it will cut here and then do some other things, okay. And here's the customer. In this case, again, you have to fill in the code for this, and he will be executing the get haircut. Now the barber thread basically runs in this while loop that it will be calling this barber here, whereas the customer thread will just basically make like customers, and we may have multiple customer threads, okay, that will be launched. The key thing is when the barber is cutting a hair, when it's executing this function, there should be at most one customer who is getting a haircut. This is basically this is the main idea of that. So we want you basically to work on this particular the problem, synchronization problem. And here's the semaphore template for the same problem, and we want to basically work on this. We define basically a semaphore on customer, and you initialize it to 0 because there's 0 customers, and you have the barber, okay. Again, it's the number of barbers waiting for customers. Here we have a mutex, okay, for mutual exclusion, and waiting is the number of customers that are in the chairs. So here's our barber thread, and here's our customer thread. Now try to solve the same problem with semaphores. Okay, so that concludes our discussion for this particular topic. And when you basically do your coding, make sure that you check a number of cases. Like for example, B, like does the barber sleep when there are no customers? BC, meaning that does the first customer wake up the sleeping barber and have his haircut? Does the second customer waits for the barber while he's giving a haircut to the first customer? Or does, if we have only 5 customers and plus 1 customer in the barber's chair, then it means that the 7th customer should be waiting. And finally, does the barber wake up a waiting customer after finishing the haircut of the first one? And is it efficient? So these are all important things, and I highly suggest that you check your code as you basically, whatever your solution you do, consider these cases and make sure that it satisfies all of them.